Welcome to our next episode of Smart Control in Practice. I'm Jackson, the Analytics Engineer at SIG Machine Learning. In our previous video, we did a comparison of how a smart controller compares to a PID controller. If you'd like to know more about this, please check out the YouTube video titled PID vs Smart Control. In today's video, I'm going to demonstrate the effectiveness of smart control when it comes to dynamically optimizing an industrial asset. Firstly, let's discuss what we mean by dynamic optimization. Dynamic optimization refers to continuously responding to changes in a system to improve its overall performance. If we take an operating gas field as an example, in this field, we require to routinely supervise these assets and also make adjustments to their control set points. Doing this helps us respond to changes that are occurring in the system. Now let's investigate what some of those changes could be and how it impacts dynamic optimization. Imagine you have a field of these assets, all in a network connected to a processing facility. Supervising and coordinating set point changes that benefit the performance of different groups can be a complex and time-consuming task, especially when there's a significant amount of assets in our network. What happens if the hydraulics of the network suddenly change due to a downstream event, such as a significant increase in inlet pressure at the processing facility? Each asset is going to need to respond independently to this change. Dynamic optimization must consider these changes that are occurring and also respond in a way that still aligns with our overall strategic objectives. As a result of this dynamic change in inlet pressures, some regions may be experiencing a sharp increase in network pressures, resulting in a need to reduce the amount of optimization. This may favor actions that are protective. Some regions may be experiencing a moderate increase, resulting in a mix of actions that lead to increases in production and another mix of actions that lead to protection. While other regions may be largely unaffected, resulting in actions that lead to favoring an increase in production. It's a complex system to manage. The solution to this problem can be achieved by leveraging smart control technology to help coordinate these changes at scale. We'll get into a bit more detail shortly. Before we do, let's break down some of the value drivers that can be achieved with a smart controller when dynamically optimizing a system. Dynamic optimization can help us maintain and enhance our production performance by identifying opportunities to maximize production rates, reduce our costs by protecting the system when regional and local events in a network introduce failure risks, and increase our engineering efficiency by coordinating changes that support the performance at a group level. Let's take a look at some other examples of dynamic optimization. As in all our videos, let's break down what we're looking at here. The following trends are of an operating gas well. Each trend is showing us data from telemetry on site, and these trends can be grouped by production rates, operating pressures, and other critical telemetry, all of which helps us understand the current and historical state of the system. The smart controller is currently operating in open loop, meaning that recommendations are being generated in the swim lane below, and the engineer is responding to the recommendations by actioning them in the control system. You will note that the production rates are responding to changes in pump speed through this period of operation. We see a small decline in production through this period here, and immediately after this, the system corrects itself and begins to reveal opportunities to capitalize on these positive adjustments and begin a cycle of increased speed recommendations. Let's point out the dynamic changes in the system that the smart controller is responding to. A negative speed step test occurs, resulting in a decline in water rate. This signals a response by the smart controller to increase pump speed and recover the shortfall. This is actioned by the engineer, resulting in a recovery in our water rate. The preceding operating periods show sustained production rate increases as a result of the increases in speed. The smart controller capitalizes on this, responding with a succession of speed increase recommendations. The engineer actions these recommendations and further accelerates production. Lastly, the smart controller is only looking to increase pump speed when the pressure drawdown rate is within a pre-configured window of operation. When these bounds are exceeded, the recommendation changes back to speed decreases to reduce the risk. Once operation is stabilized again, the smart controller changes back to speed increase recommendations to continue enhancing production performance. So what is the difference between the manual engineering operation and the smart controller supervision? The manual set point adjustments are made at a slower rate compared with the recommendations from the smart controller. The smart controller generates recommendations that capitalize on the positive adjustments in water and gas rates, while remaining conservative when there are dynamic changes in the system that can increase the risk of failure. This series of smart controller recommendations demonstrates an example of where production could have been accelerated, all while considering the constraints we impose on the system. In our next episode, we'll be looking at an example of how a smart controller can help to reduce emissions. In the meantime, if you'd like to know more, please reach out to the team. Catch you next time.